One of the largest remaining Southwestern Willow Flycatcher populations breeds along the Rio Grande in New Mexico. Back in 2015, we had seen the impacts of Diorhabda on swivel breeding habitat in other parts of the Southwest, and we're starting to hear reports of the beetle on the Rio Grande, but hadn't yet seen it in occupied swivel habitat. But we knew it was only a matter of time. So that year, 2015, we began a Diorhabda impact monitoring study in occupied swivel habitat on the Middle Rio. Sure enough, in 2016, Diorhabda was observed throughout the Rio Grande, including at some of our monitoring sites. This is the map I'm sure everyone here has seen that Rivers Edge West puts together every year, showing Diorhabda locations by year. This map includes 2007 to 2019 observations, with the 2019 Diorhabda locations in blue. We work here on the Rio Grande from approximately Albuquerque to El Paso, and Diorhabda had colonized this entire area by 2016. So it seemed important to initiate this study because Diorhabda is likely to have a significant negative impact on swivel habitat in the Rio Grande, where, like most modern day swivel habitat, salt cedar is a major component. Although the Rio Grande floodplain was historically native dominated due to changes in hydrology and vegetation composition, salt cedar has overtaken willow in its dominance of the riparian ecosystem. This graph shows the percentage of nests constructed in salt cedar versus willow over the last 2 decades. And as you can see, it shifted from approximately 75% of nests constructed in willow back in 2002 to about 2/3 to 3/4 of nests constructed in salt cedar currently. Likewise, about 75% of breeding territories are either salt cedar dominated or have a salt cedar component. So we're using photographic monitoring to quantify beetle-induced changes in canopy cover and vegetation community structure in swivel territories. So hemispherical photos are taken from within the riparian vegetation, facing upwards at the vegetation canopy using a fisheye lens. And landscape photos are taken with a normal lens facing inwards towards the vegetation community. And then we use a software program that's designed to classify the hemispherical photos and calculate canopy cover. 2015 and 2016 provided pre-impact, pre-Diorhabda defoliation data in most of our sites. We did not observe Diorhabda in our monitoring sites until 2017. So typically, as is likely intuitive to everybody here, canopy cover increases throughout the growing season. So this graph shows the seasonal progression of canopy cover in our native dominated control site, as measured by hemispherical photography. So we take photos 3 times per breeding season in May, June, and July. And as would be expected, canopy cover increases throughout the summer as vegetation leaks out. However, we see the opposite trend in sites impacted by Diorhabda. So this graph shows canopy cover as measured by hemispherical photography in one of our monitoring sites that's been hit hardest by the Tamarisk Beetle, DL12 North. And I'm going to continue to use this site as the example throughout this talk. So as you can see, canopy cover declines throughout the breeding season as defoliation occurs. In May of 2017, there had been no defoliation in this site yet. In that first year of defoliation, canopy cover starts around 92%, and by July of that year, it declines to about 85%. In the second year of defoliation in that site, 2018, average canopy cover for the site starts a little bit lower, just under 90%, and continues declining even further to just over 80% on average by the end of the season. Now, Diorhabda did not colonize this site in 2019 or 2020, giving the habitat a chance to recover. However, despite 2 growing seasons without defoliation, the site still has not recovered to pre-Diorhabda canopy density, And instead, canopy cover seems to hover around 85 to 90%. So this line shows average canopy cover for the site prior to any defoliation. And again, it was over 90%. And despite 2 years without defoliation events, the site has not returned to that level of canopy cover. So we'll come back to why this might be later. So now I'm going to show you what the landscape photography looks like. And these photographs really give an excellent depiction of what that defoliation-induced decline in canopy cover that we just saw graphed really looks like in the habitat. So this first photo is DL12 North, same site I just showed you the graphs for, in May of 2017, prior to any Diorhabda defoliation. By July of 2017, this is that same location. So these are photographs taken from a fixed point. And by July of 2018, after a second year of defoliation, this is how the habitat looked. So I want to point out here that hemispherical photography cannot distinguish between live and dead vegetation. As you can see in these second two photographs, there's still quite a bit of dead foliage, dead foliage on the salt cedar. But the difference between live and dead foliage is likely significant to a nesting bird. So when hemispherical photography indicates 80% canopy cover, that habitat can actually look quite poor despite what sounds like a fairly high cover percentage. So remember, those previous graphs, hemispherical photos showed us that average canopy cover of the site was 92% in May of 2017 and declined to about 80% by July of 2018. But clearly this looks like a much larger than 10% decline when you actually look at it. And then finally, this last photograph shows the same location in July of 2020, after 2 seasons with no defoliation. Clearly, there's been significant habitat recovery. But if you look closely, as we see with the hemispherical photography, it's still not returned to the pre-defoliation levels. So if you compare those first and last photos in the series, you can see, for example, in July of 2020, there's much more sky visible. You can see those exposed tree trunks in the last photo. So clearly the vegetation has not recovered to the same density that we saw in May of 2017. In addition to taking hemispherical photos throughout the breeding season, we also took photos once per winter as a means of measuring woody mass and determining what percentage of breeding season cover was foliage. So when we took these photos in the winter, there was no foliage on the trees. This is just cover due to branches, tree trunks, woody mass alone. This graph shows average dormant season canopy cover in DL12 North, our same focal site here. And there's a few things of interest that I want to point out. One is that a high percentage of cover in these sites is comprised of woody mass alone, right? So if you look at the 2017 photos on this graph, a little over 80% on average canopy cover is measured in the winter. So that means when we see 92% cover in the summer, you can kind of do some back of the napkin math and figure out how much of that is foliage. But when we see breeding season cover drop to nearly 80%, that translates to very little foliage left on the trees. The other thing to notice here is the obvious decline in woody mass over time. So again, this graph is not within the breeding season. This is dormant season cover across years. Diorhabda is expected to slowly kill salt cedar through the stress of repeated defoliation, which leads to the loss of woody and root mass. And that's exactly what we're seeing here. Particularly after the second year of defoliation in 2018, we see this big drop in woody mass. And this can, again, be compared to our control site, less than a kilometer south, where woody mass essentially stays the same over time. So this control site is predominantly coyote willow, So we had a wet year in 2019. We see this slight increase in woody mass, and then it kind of declines a little bit. But essentially, woody mass in this site stays more or less the same over time, which is what we'd expect, compared to this steep drop off in DL12 North. So I said earlier we would come back to the fact that although it's been 2 years without defoliation in these monitoring sites, the vegetation still not returned to pre-Diorhabda health, as we saw through hemispherical and landscape photos. It seems like there's likely a few things going on here. First of all, we saw that the stress of defoliation led to declines in woody mass, and this contributes to an overall reduction in canopy cover. However, just looking at these two photos, one of May in 2017, one in May of 2020, you can see there's an overall decline in foliage density as well. Additionally, we've observed declines in canopy cover in some of our monitoring sites that were not impacted by Diorhabda. So it seems likely that the vegetation is simultaneously being stressed by drought and a dropping water table, as well as Diorhabda. So in some sites that aren't impacted by Diorhabda, drought alone is enough to cause decline in vegetation health. But there appears to be an interactive effect of drought and defoliation in some sites that's causing these severe declines in vegetation health and a lack of recovery even in the absence of defoliation events. So in addition to photographic monitoring, in 2018, we began quantifying vegetation composition and density at our monitoring stations in 3 different height class in order to track potential longer-term changes in the vegetation community. Just very briefly, although we only have 3 years of data at this point, our initial results suggest that there are increases in dead vegetation at the sites that have been impacted by Diorhabda that seem to correspond with nearly identical decreases in salt cedar. So the dark bars on this graph are showing the increases in dead vegetation over time. The lighter bars are showing decreases in salt cedar. We do not see a corresponding increase in other types of woody vegetation, such as coyote willow. We're just seeing this increase in dead vegetation. So these changes in canopy cover and vegetation composition we've been discussing can affect breeding flycatchers both directly through loss of nest concealment, as well as indirectly through changes in microclimate. So we deployed data loggers to measure temperature and humidity at our hemispherical photo stations. Each line indicates one photo station within a single site. So each of these lines here is within a single site. This is our control site. We see little variation in maximum temperature between photo stations within a site at our control site. So native dominated vegetation here. And maximum temperatures of approximately 85 to 95 degrees. However, at defoliated site, we see a noticeable difference in maximum temperature between photo stations within a site. And keep in mind, these photo stations are only about 50 to 75 meters apart. So the difference between points lies in the percentage of the vegetation at that point that's comprised of salt cedar compared to other species. So those points depicted by the lower 2 lines in the graph had minimal salt cedar and therefore also minimal defoliation. And maximum temperatures remain low, similar to the 85 to 95 degree range seen in the control site. However, the 3 points depicted by the upper 3 lines on the graph, the blue, green, and purple, were dominated by salt cedar, nearly 100% in some points. These locations were severely defoliated by Diorhabda, and maximum temperatures here were much warmer than at the other 2 points in the site, often over 100 degrees. So again, these differences are likely very important to a bird trying to regulate their own temperature, as well as the temperature of their eggs and offspring. We saw similar patterns in minimum relative humidity, such that defoliated sites were more arid. In other words, despite a relatively small decline in canopy covered, only about 10% or so, there's a measurable increase in temperature and humidity. So a small loss of canopy cover can have a severe impact on breeding willow flycatchers, both directly through the loss of nest concealment and indirectly through a loss of suitable microclimate conditions for nesting. And clearly you can just see the difference in this front photo where the nest circled here in red is in fully foliated salt cedar compared to the other two where the salt cedar they're nesting in is being defoliated. So of course the big question here is, how is this affecting the birds? And this graph shows the number of nests and nest productivity in Dale 12 North over the last several years. Although we need additional years of data to really determine a long-term trend, the data we do have suggests a slow overall decline in both nest numbers and productivity in this site. And even just anecdotally, the habitat in the site does appear to be declining in quality. However, we haven't seen as steep a decline in habitat conditions in all of our monitoring sites that have been impacted by Diorhabda. The take-home message here is that Diorhabda certainly negatively impacts habitat quality for willow flycatchers during defoliation events. And the stress to vegetation can be severe enough to prevent immediate recovery in the absence of Diorhabda. In addition, those impacts can be interactive when combined with other environmental stressors, such as drought, making the impacts of Diorhabda more severe and longer lasting than what we might see due to defoliation alone, as well as uneven across breeding areas as environmental conditions might vary. So in many cases, not only does it appear highly unlikely that other non-salt cedar woody species will quickly, or in some cases ever, take over the space opened by dying salt cedar, our data suggests that simply removing Diorhabda from the impacted habitat might not be enough to facilitate the recovery of the habitat and the vegetation that's already there to its pre-Diorhabda state. And so with that, I can take any questions if I have any time left.